So in working problems with energy, what we've said we want to do is learn how to recognize what energies are present in our system and then learn how to keep track of them. And so for the mechanical energy systems that we're dealing with right now, what types of mechanical energy do we need to keep track of? Well, the first one is the kinetic energy. And that one's relatively easy to recognize because it's the energy due to an object's motion. So if the object is moving, then we need to keep track of its kinetic energy. The second energy that we're going to keep track of is the potential energy. The potential energy we're going to represent with the letter U. It's the energy an object has due to its position. Or another way to say this is it's the energy a system has due to its configuration. And what we'll see is that we'll learn to recognize when this energy is present based on particular types of forces that are going to do work within the problem. So our general definition for work is that work is a transfer of energy due to a force acting on an object to cause or hinder some displacement. So if an object moves, the forces that act on that object can do work on that object as it's displaced. But we can break this up into two types of work. So the first type is work that goes to add or subtract energy from the system. So this is a transfer of energy either into the system, increasing the energy, or out of the system, decreasing the energy. The other type of work that we can have is work that's done to convert energy from one form to another. So in this type of work, the energy transfer is within the system, which means the total energy of our system doesn't change. Instead, it's transferred from one of these forms, say kinetic energy, to another potential, or go the other way around and convert it from potential to kinetic. So what types of forces do each of these types of work? It works out that what we can call non-conservative forces, so that's the little NC subscript here, that the work done by non-conservative forces goes to changing the energy of your system. So when non-conservative forces do work, they're going to transfer energy into out of your system, either increasing the energy of your system or decreasing the energy of your system. On the other hand, conservative forces, that's what our little C subscript is here, the work done by conservative forces converts energy from one form to another. So part of why conservative forces are known as conservative forces is precisely because the work they do doesn't change the energy of the system. The energy of the system remains constant when these forces do work because it's simply transferring it from one form to another. If the energy of your system doesn't change, that means the energy of your system is conserved. How do we define the change in the potential energy? Delta U, the change in potential energy, is equal to negative the work done by a conservative force. So what this means is that the potential energy of a system is describing energy available to the system due to its configuration. And where does that energy come from? It's due to the fact that the object was initially displaced in the opposite direction that the conservative force was pushing or pulling the object. So in moving in the opposite direction that the conservative force was pushing or pulling, that means that the conservative force did negative work. If the work term is negative and you multiply it by this minus sign out front, those two negatives cancel, and that goes to increasing the potential energy. So one of the things we want to understand is that you increase the potential energy of your system by moving against the conservative force. If you want to get that energy back, so again, convert that potential energy into kinetic energy, then the conservative force must be allowed to do positive work on the system. And again, that's coming straight out of this equation where if the work done by the conservative force is positive, and then you multiply that positive value times this negative sitting out in front, and that tells you that the potential energy is going to decrease. Delta U will be negative. The more you increase the potential energy of the system, the more you increase the opportunity for the conservative force to do positive work. As you increase the potential energy of your system more and more, what that means is that more and more negative work was done by the conservative force, which means there's more opportunity now for the object to move with the conservative force, get that potential energy back, converted into kinetic energy. In mechanics, which forces that we've talked about so far in this course are conservative forces? Well, there are two of them. The first one's the gravitational force. We can keep track of the work done by the gravitational force by thinking about the gravitational potential energy. The second force is the spring force, or the elastic force. And again, you can think about the work done by the spring force that's related to the change in the elastic potential energy of your system. Well, which forces are non-conservative? The short answer is everything else. So gravitational force, spring force, these are our conservative forces at this point in the course, and every other force that we've talked about, the normal component, friction component, applied forces, tension forces, all of those are non-conservative forces. So again, thinking about our definition for the change in the potential energy. Is there a way that we can figure out whether the potential energy of our system is increasing or decreasing by thinking about how our system is changing? The way we want to get comfortable thinking about this is, are you moving with or against the conservative force? So if your object is moving against the conservative force, it will increase the potential energy of your system. If the object is moving with the conservative force, that will decrease the potential energy of the system. So if the object moves in the direction that the conservative force pulls on it, well, what that means is that the conservative force is doing positive work. That positive work multiplied by a negative means you're decreasing the potential energy. So again, if you move in the direction the conservative force pulls on your system, that means you're moving with the conservative force, and in that case, the potential energy decreases. On the other hand, if your object moves in the opposite direction that the conservative force is pulling on it, so it now moves against the conservative force, then the work done by the conservative force is negative. Again, negative work term times the negative sign out in front tells you that delta U is positive, which means that the potential energy increases. So again, whether or not your object is moving with or against the conservative force tells you whether or not the potential energy of your system is increasing or decreasing. So to increase the potential energy, you have to do positive work against the conservative force. So if the conservative force is doing negative work, that's because there's some external agent that's moving your system around doing positive work, and that positive work goes to increasing the potential energy, which again you can then get back by letting your system go. In terms of thinking about our two conservative forces, well, we know that the gravitational force points down. So to move against the gravitational force means your object needs to go up. So you increase the gravitational potential energy by lifting an object. If you drop an object, well, now it moves with the gravitational force. Both of those point down, and you would decrease the gravitational potential energy. Spring force, we know, always points back towards equilibrium. So again, you increase the elastic potential energy of your system by stretching or compressing your spring even further. So moving the mass attached at the end of your spring further away from equilibrium. In that case, you're moving it against the spring force that's pointing back towards equilibrium, which means you're increasing the elastic potential energy. When you let that mass go, then it's going to move back towards equilibrium, which means it's moving with the spring force, and so therefore it's decreasing the elastic potential energy.